Hello and welcome to this summary video on the entirety of my particle physics series. This is just one handy little video which has all the other particle videos in, with all the beginning and ending crap cut out of it. And also in this video attached in the description is the summary notes for the entire thing. So hopefully you enjoy. So let's talk about the basics. Every atom has a nucleus which contains protons and neutrons. Both of these particles are known as nucleons. Orbiting the nucleus are electrons. One of the definitions you're going to have to know is the proton number, or the atomic number, and this is the amount of protons in the nucleus. In a neutral atom, this equals the amount of electrons, so it can tell you about chemical properties and such. The nucleon number, also the mass number, is the amount of protons and neutrons, aka the amount of nucleons inside the atom. And here's just sort of a brief visual sort of representation of what I'm talking about. In this carbon-12 atom, the proton number is specified at the bottom left, and the mass number is specified on the top left. Essentially to the left of the symbol of the atom, or the element. Next thing is isotopes. These are atoms with the same number of protons, but different number of neutrons. So same proton number, different nucleon number. Here's an example. Hydrogen has 3 natural isotopes. You can find hydrogen with 1 proton and 0 neutrons. This is known as hydrogen. Or 1 proton and 1 neutron. This is known as deuterium. I'm going to be butchering pronunciations all over the place. Or with 1 proton and 2 neutrons. Tritium, this is called, I think. The chemical properties aren't changed if you change the amount of neutrons. Chemical properties are associated with the amount of electrons. The only thing that is changed is the stability of the nucleus. Once you start crapping around with the amount of neutrons, it's stability that's affected. Unstable nuclei is dodgy territory, as they can be radioactive and decay over time into different nuclei that is more stable. Radioactive isotopes are kind of useful though. It's how we're able to date things. You see, all living matter contains the same proportion of the radioactive carbon-14 taken in from the atmosphere, the normal one being carbon-12. Me and my friend here both have roughly the same amount of carbon-14 taken in from the atmosphere. And although we look 200 times more stupid than this swan also, believe it or not, has roughly the same amount of carbon-14 taken in from the atmosphere. Now, when we cease to exist, so when me and my friend die, the amount of carbon-14 inside of us decreases over time as it is decaying. Using the isotopic data to find the percentage of radioactive carbon-14 that's left inside of us, scientists can calculate the approximate age of our dead corpses. Last thing I'm going to talk to you about is specific charge. This is the ratio of a particle's charge to its mass, which is measured in coulombs per kilogram. So essentially, as you may be able to guess, to calculate specific charge, you just divide the charge by the mass. Amazing. So, here's just a little example. A question you might be asked is the specific charge of a carbon-12 nucleus. Okay? So, let's work out the mass. The mass is basically 12 nucleons. So, and the mass of a proton and neutron is the same, and that is 1.6 times 10 to the minus 27. That value will be given to you in the datasheet, so you don't have to memorize that, don't worry. So it's 12 nucleons, so 12 times 1.67 times 10 to the minus 27 equals 20.04 times 10 to the minus 27 kilograms. That 1.6 times 10 to the minus 27 is in kilograms. Next, let's calculate the charge. And because this is just the nucleus, we don't take into account the electrons, okay? So there are 6 protons in the nucleus, so that's 6 times the charge of a proton is 1.6 times 10 to the minus 19. That value will also be given to you in the datasheet. The charge of an electron is obviously the same thing, but minus. And that equals 9.6 times 10 to the minus 19 coulombs. Now to calculate specific charge, we just divide the charge by the mass, which gives us the resulting 4.79 times 10 to the 7 coulombs per kilogram. Remember, units are important. And the second thing that's important is significant figures. The lowest amount of significant figures given to us in this question were 3. That's given from the 1.67 times 10 to the minus 27 and the 1.6 times 10 to the minus 19 values. Those figures are to 3 significant figures, and there's no really other value that we can take into account, so we'll use 3 significant figures as our sort of base. So we will leave our answers leave our answer in 3 significant figures. Now, this is quite a complicated concept, so probably the best way to explain this is to have the diagram, this very, very helpful diagram up, whilst I explain it. Feel free to pause and just sort of take it in both before and after I explain it. I think that would be the best way to do it. So I mean, as we know, the electrostatic force exists in the nucleus, but if this was the only force, the nucleons would just start flying apart. So we know there must be a force that exists in the nucleus that is stronger than the electrostatic force. This is the strong nuclear force, or the strong interaction. Experiments have shown that the force in fact has a very short range of approximately 0.5 to 3 femtometers. It's also been shown that the force works equally between all nucleons, meaning the size of the force is the same between protons and protons, neutrons and neutrons, or protons and neutrons. So as you can see, the strong nuclear force is repulsive for very, very small separations of nucleons. That is what's sort of like stopping them from just colliding and, collapsing into each other. And then as the separation increases past 0.5 femtometers, the force becomes attractive, which sort of holds them together, stops them from flying apart, and reaches a maximum attraction value, I think that should be. And then it just falls rapidly towards 0 after about 3 femtometers. The electrostatic repulsion always exists. It is completely indefinite. It's very high when the strong nuclear force is very high, and then it's very low when the strong nuclear force is also low. One way to remember the range, this is how my physics teacher taught me it, is pretend you're in a bar, right? You've had a few drinks, it's pretty dark, and you're about 3 meters away from this girl, and you're just like, oh, all right, she looks pretty good. The closer you get to her, the more your sort of excitation of the idea of being with this girl builds, so your attraction is building. Once you get to about 0.5 meters, or femtometers in this case, you're just like, oh, yeah, you looked a lot better from the other side of the room, and you are completely repulsed. So, the strong nuclear force kicks into repulsion. That is the way I remember it. Next thing is alpha emission. This only happens in massive nuclei, so like uranium and radium, and this is because they have too many protons. The nuclei of these atoms are just too huge for the strong force to keep them stable. An alpha particle is basically just a helium nuclei, as 4 nucleons, 2 protons, so 2 protons and 2 neutrons. And when a alpha particle is emitted, the proton number decreases by 2, and the nucleon number decreases by 4. So as you can see, it has a really, really, really short range. So as you can see in this example, uranium has a nucleon number of 238 and a proton number of 92, then loses 2 protons and becomes a completely new element, which has a nucleon number of 234, and then we also have our alpha particle, which, as I said before, is basically just a helium nuclei. Next thing is beta minus emission. At GCSE, you might have heard of, you will have gone through beta emission, but there is beta minus and there is beta plus. But right now we're going to talk about beta minus. Basically, it happens in neutron-rich isotopes. So, unlike alpha emission, instead of too many protons, this is too many neutrons. A beta particle is basically just an electron. Basically, it's the emission of an electron from the nucleus along with an electron antineutrino. Yes, a bit of a mouthful, but give me a minute. Which is released in order to conserve energy and momentum. When a nucleus ejects a beta particle, one of the neutrons in the nucleus is changed into a proton. And so the proton number as a result increases by 1, and the nucleon number stays the same. Beta particles also have a much larger range than alpha particles. And here's an example. We have an element of a proton number of 75 and a nucleon number of 187. One of the neutrons turns into a proton, and this results in the proton number increasing by 1. The nucleon number stays the same because the proton turning into a neutron doesn't change the nucleon number because they're both nucleons. And of course we have our beta particle, aka an electron, and an electron antineutrino. History of the neutrino. Nice little story. So scientists originally thought that beta decay only emitted an electron, but they were wrong. Observations showed that the energy of particles after the beta decay was less than it was before, which didn't fit in with the principle of conservation of energy. Every interaction must conserve energy. A lad named Wolfgang Pauli, look how hard he looks, you would not want to mess with him. You really wouldn't. So, in 1930, he hypothesized that there was in fact another particle being emitted, which was carrying away some of the missing energy and momentum. And that this particle was obviously neutral in order to satisfy conservation of charge laws, because charge also has to be conserved in every single interaction. Other discoveries in the future then led to Pauli's theory becoming accepted, and the particle was classed as a neutrino and was eventually actually observed 25 years later. So although the neutrino was not seen for 25 years, people didn't really want to disagree with this guy. Firstly, let's begin with photons. Photons are packets of electromagnetic radiation, and if you don't know the electromagnetic spectrum, then here it is. There's also a song that accompanies this. I think I can hear it in the distance. I'll leave a link to that song in the description. It actually is really helpful. I've had this spectrum memorized since, well, it's been about 2-3 years now. Anyways, electromagnetic radiation exists as photons of energy, to packets basically. The energy of a photon depends on the frequency of the radiation. Now that we got that out of the way, we can get into the nitty-gritty fun stuff. The antiparticles. Every particle has a matching antiparticle with the same mass and rest energy, but opposite charge. Here's a nice little table. So each antiparticle is basically called anti-whatever, and has a line above the symbol to signify the antiproton. The exception here is when we come to the electron. Because the anti-electron is so common, we decided to give it a shorter name, and that is the positron. And instead of a line above, we just signify that it has a plus charge as opposed to a minus charge. And as you can see, the relative charge and mass is the same for each particle and their corresponding antiparticle, but of course the only difference is the relative charge. So we can actually create a particle and antiparticle pair from energy. This is called pair production. Pair production only happens if a photon has enough energy to produce that much mass, and only gamma ray photons have that kind of energy, because two particles from just a photon, that you gotta have a lot of energy to create that kind of mass. It also tends to happen near a nucleus, which helps to conserve momentum. The usual combo is an electron-positron pair because they have a relatively low mass, and this is how it's displayed. The minimum energy for a photon to perform pair production is the total rest energy of the n particles produced. Each particles have a rest energy of E0, so as you can see, there's 2 particles produced, that's why it's E times 2. Next is annihilation. In essence, this is the complete opposite of pair production. When a particle meets its corresponding antiparticle, annihilation results, and the combined mass of the particles get converted into energy. So, theoretically, if you had yourself cloned, but all, your protons and electrons and neutrons, basically all your matter was antimatter, so in essence, an anti-you, if you two collided, you'd just disappear and turn into energy. How fucking cool is that? But the key thing to remember here is that 2 photons are created as a result, okay? This is to conserve the energy momentum, and the formula is pretty much the same, except it's just E. Not 2 times E, it's just E. Today, I'm going to be teaching you about classification. Here's a nice little classification tree of particles. We have hadrons, which are then subdivided into baryons and mesons, and we also have leptons. So why don't we kick off with the hadrons? These are basically particles that are classified as being affected by the strong nuclear force. That's it. That's literally all there is you need to know about hadrons. But as you know, they are split up into baryons and mesons, and there is a lot more to learn about baryons and mesons. Let's get started with baryons. What do we need to know about baryons? Well, their defining trait is they are made up of 3 quarks, and don't worry, quarks will be covered in a future video. Two examples are protons and neutrons. These are the only two baryons that we need to know about according to specification. And the proton is actually the only stable baryon. All baryons try and decay into a proton because it is the most stable. It's like that one kid when you were little who had all the games consoles and all the games and all the controllers, and everyone would go around to his house and you always envied him. You always wanted to be that kid. Yeah, well, you know, that kid was the most financially stable, so obviously everyone wants to be the most stable. Anyways, what about antiprotons and antineutrons? Yes, they exist and they are known as antibaryons, yeah. All baryons have a baryon number of 1. Baryon number is a quantum number that must be conserved in all interactions, so this is very important. Baryons have a baryon number of 1, non-baryons have a baryon number of 0, and antibaryons have a baryon number of -1. And like I said, baryon number needs to be conserved in all interactions. Interactions are also coming up, I think it's the next video. Anyways, let's move on to mesons. Now, the main difference between baryons and mesons is that mesons are only made up of 2 quarks, a quark and antiquark pair. The 2 mesons we need to know about are pions and kaons, but this can include pi plus, pi minus, neutral, pi neutral, k plus, k minus, and k neutral. If you're asked what the antiparticle of a pi plus particle is, then it's just a pi minus. The antiparticle of a k minus is just a k plus. The antiparticle of a pi neutral is just a pi neutral. All mesons want to be a pion because that's the most stable. It's literally the same concept as the baryons and the proton. Literally, kaons are just heavier pions and more unstable. So essentially, the kaon's fat and wants to be a pion as a result. Anyway, let's move on to leptons. Leptons do not feel the strong nuclear force. Just to clarify, leptons and hadrons feel the weak force. Everything in existence feels the weak force, alright? But hadrons are the only things that feel the strong nuclear force. They're not made of quarks, they are fundamental particles. Okay, you cannot categorize leptons even further than leptons. That is as lowest you can go. The electron is an example of a lepton, and muons and neutrinos. Muons are basically, again, same thing with decay on the pion. Muons are like a heavy electron, but they eventually decay into a standard electron. Electrons and muons have their own neutrinos, so you have the electron neutrino, anti-electron neutrino, as we saw in the previous video, the video before, whatever, one of the videos. We have the muon neutrino, anti-muon neutrino, you know. Again, lepton number is another quantum number we do need to be aware of. Leptons have a lepton number of 1, non-leptons have a lepton number of 0, anti-leptons have a lepton number of -1. Lepton number also needs to be conserved in all interactions, but one thing we do need to know is that electrons and muons, they have their own sort of separate lepton number. So in an interaction, the lepton number may be conserved, but you may have a mismatch with the electron lepton number and the muon lepton number, so you do need to be aware of that. So, interactions between particles are caused by a particle exchange. When two particles interact, something happens to a particle to let it know that the other one is existing. Repulsion and attraction can be explained by the bowling ball. As you can see, if someone throws a bowling ball, they're going to be pushed backwards, and whoever catches the bowling ball is also going to be pushed backwards. So, the bowling ball is essentially the concept of an exchange particle. And the two, let's say, humans on the little boats, they're examples of particles. And attraction can be explained by the boomerang example. So, the boomerang in this case is the exchange particle. So, one particle will throw the boomerang facing the other direction. He'll throw the boomerang, which pulls him back, and the other one will catch it, which will throw him back. These exchange particles are called gauge bosons, which are virtual particles. There are 4 fundamental forces in nature. Gravity's crap, so no one's really bothered about it, but here are the rest and their corresponding gauge boson. As we learned from the classification video, the strong force affects only hadrons, and the weak force affects everything. But as you may have studied in chemistry, the electromagnetic interaction also exists, and it exists between charged particles. That's the interaction between electrons and protons in an atom. So the gauge boson for the electromagnetic is a virtual photon. For the weak force, it's a weak boson, weak plus and weak minus. And for the strong force, the boson is actually pions. So the pions are the exchange particle in a strong interaction. The W plus and W minus are the exchange particle in weak interactions. And the virtual photon are the gauge bosons in the electromagnetic interaction. The W bosons have a ridiculous mass. It's about 100 times that of a proton. Not a photon, but a proton, which then results in a very short range. Because of this ridiculous mass, creating a W boson uses so much energy, it can only exist for a short amount of time, and as a result can't travel that far. And vice versa is the case with photons, which have absolutely no mass, and so as a result we get an infinite range and a really, really long time of existence. Let's move into the nitty-gritty stuff, and that is Feynman diagrams. These were created by a gentleman called Richard Feynman, known as one of the greatest physicists of all time. Richard Feynman has a plethora of volumes of physics books. If you've got no life, like me, then you'll find them very, very interesting. I would recommend giving them a read. But anyways, so this guy, he created these diagrams which help better display particle interactions, although he did have a couple of rules. Incoming particles start at the bottom of a diagram, and they travel upwards. Time is represented upwards. So, yeah. Baryons and leptons have to stay on their own sides. They can't cross sides. Charges on both sides must balance. Gauge bosons are represented by wiggly lines, and yes, this is the proper technical term. You can say wiggly line in your exam. And all standard particles are represented by straight lines. So, let's have a look at a couple examples. And these are the main examples you're going to need to know. So first of all, let's look at electromagnetic repulsion between electrons. So as you can see, there are arrows signifying the direction of the electrons, and as you go further in time, the electrons are moving closer together, but once they hit that virtual photon, once that virtual photon tells both of the electrons that each of them exists, they're like, whoa, 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 I want no part of you, and obviously, if a particle has the same charge, then it's just going to repel each other, as you can see. Also, as you can see, the exchange particle is represented by, in fact, a wiggly line, and time moves upwards. Same thing with positrons as well, or protons. Any particle with the same charge can represent electromagnetic repulsion. So, in electron capture, a proton interacts with an electron, and as you can see, it obeys the whole, baryons on one side and leptons on the one side. The protons and neutrons are on the left side. The electron and electron neutrino are on the right side. But this isn't the electromagnetic interaction. As you can see, there are neutrally charged particles in there. So this is an example of the weak interaction. As a result, we have a W plus boson. The reason it's W plus is because, as you can see, the arrow is coming off the proton. It's going towards the electron side. The proton conserves its whole plus charge, and so as a result, you've got a W plus boson. And again, arrows on each of the particles to show which direction they're going, and of course, time moves upwards. The last one is beta minus and beta plus decay. Obviously, there's two of them, but they're pretty much the same thing. So we'll start off with beta minus. As you can see, a neutron turns into a proton. However, the neutron needs to conserve a minus charge because the electron is negatively charged. So you've got a W minus boson, which then kicks off into an electron and anti-electron neutrino. And they're pretty much the opposite thing with beta plus decay. A proton, conserving its W plus charge, turns into an electron and turns into a positron and a electron neutrino, and turns into a neutron. Baryons on one side, leptons on one side. It's complicated business, but it's also simple business once you memorize the rules. Now, in chemistry, you may have learned, the proton is a fundamental particle. A neutron is a fundamental... No. Don't listen to any of the bollocks chemists tell you. Quarks are fundamental particles and are the building blocks for hadrons, and consequently, antibaryons and antimesons are made from antiquarks. The three we need to know about are the up, down, and strange quarks, and of course their respective antiquarks. We're also given the quantum numbers for all of these in the datasheet in the exam. There are actually 6 quarks. The other 3 are charm, top, and bottom, but we'll focus on up, down, and strange. As you can see, the charges and baryon numbers of all of these are in thirds, but as we know, particles need to have a whole number of charge, so that's why some quark combinations just do not work. Let's talk about baryons. As we know, baryons are made up of 3 quarks, and here's how. If we look at how a proton and an antiproton are made, a proton is made up of up, up, down. This is because the total charge adds up to 1, as you can see, and the baryon number adds up to 1. 3 quarks is always going to give you a baryon number of 1. It's inevitable. Unless, of course, antiquarks. As you can see with antiquarks, all the quantum properties are shifted. Instead of the up quark having 2/3 charge, it's got minus 2/3 charge. And the anti-up, once again, has minus 2/3 charge. And the anti-down, instead of having minus 1/3, has plus 1/3, which results in a total charge of minus 1. All the antiquarks have baryon numbers of minus 1/3, so therefore that's why the antiproton has a baryon number of minus 1. We can do the same thing for the neutron. Up, down, down, that adds up to a total charge of 0 and a baryon number of 1. And the anti-up, anti-down adds up to, once again, a total charge of 0, but a baryon number of minus 1. Let's talk about how mesons are made. Well, baryons are just made up of up, anti-up, anti-down, down, anti-up, down, anti-down. It's just made up of a combination of up, down, and their antiparticles. That's it. All mesons have to have a quark and an antiquark pair. That's all it is. Kaons, however, they have strangeness, so they always contain a strange quark with either an anti-up or an anti-down, or an anti-strange quark with an up and or down quark. Now, strangeness is strange, okay? That's why I've been dodging the topic for a while. It's just a quantum property, a quantum number. It's a property that all quarks have. Like baryon and lepton number, all particles have this property. Unlike the baryon number and lepton number, however, strangeness is not always conserved. It's only conserved in the strong interaction. And of course, a particle with strangeness of 1 will have an antiparticle of strangeness minus 1. It works the same way in charge works and all that. It's just a fancy quantum number. That's it. The lone quark? No, you cannot get a quark on its own. No. Let's move on to an exam question. This is a question that I had in my most recent exam, and I thought it was quite a good question, so I thought I'd bring it up. Now that we've got all of our knowledge on baryons, mesons, classification, quarks, interactions, everything, we've got all of our knowledge sorted. Let's bring up this question. So, we've got this interaction. We've got a negative kaon interacting with a proton. That goes into a positive kaon, a neutral kaon, and X. We don't know what X is. However, we're also told that strangeness is conserved in this interaction. So we need to find out what X is. The way we do this is we essentially deduce the quark structure of it, okay? So the first thing we should look at is charge. Alright, well, what's the charge on the left side? Kaon has a charge of minus 1, and proton has a charge of plus 1. So we've got charge of 0 on the left side. On the right side of the interaction, we've got kaon has a plus charge, K neutral has 0, so far we're on plus 1. We then need X to have a charge of minus 1 for the charge on both sides to be equal, 0, 0. So X must have a charge of minus 1. So now from this we know that the quarks must add up to a minus 1 charge. Okay, let's deduce whether this is a baryon or a meson. We know it's not a lepton because we're told strangeness is conserved. So, is it a baryon or is it a meson? Well, the baryon number on the left side is 1, because a kaon isn't a baryon, but a proton is. So we've got a baryon number of 1 on the left side, and a baryon number of 0 on the right side. So X must be a baryon. There must be, and from this we can deduce that there must be 3 quarks. We're also told that strangeness is conserved. So let's deduce the strangeness of each side. So K minus has to have a quark structure, which includes 2 quarks, because it's a meson. It has to be a quark anti-quark pair. It has to have a strange quark, and it has to total up to minus 1. The combination that works here is the strange anti-up. And a strange quark has strangeness of minus 1, so the left side has strangeness of minus 1. If we look at the right side, I mean the K plus is the antiparticle of K minus, so it must have the opposite strangeness, which is 1. Now the K0, being its own antiparticle, has 2 different quark structures. It has strangeness of minus 1 and strangeness of 1. It can have, either. Whatever it pleases. So on the right side, on the left side we have strangeness of minus 1. On the right side, we can either have strangeness of 2 or a strangeness of 0. So X must have a strangeness of minus 1 or minus 3 to be able to conserve charge here. Let's bring up our little quark table. The combinations that work here, if strangeness is minus 1, then the combination that works here is strange down down. That gives a baryon number of 1, gives a charge of minus 1, and a strangeness of minus 1, so it works. If X is going to have a strangeness of minus 3, then a strange combination would work. That once again has a baryon number of 1, a charge of -1, and strangeness of -3. So either of those quark combinations can be X. Now, you'll notice that we didn't name this particle, we just gave it the quark structure. That's the thing, sometimes the exam's going to be sneaky, and sometimes you won't have to know what the name of a particle is, you just need to be able to deduce the quark structure. So, if you have a metal, so here we have an iron block, and you shine a light of high enough frequency onto the surface of the metal, electrons shall be emitted. How this works is that the free electrons on the surface of the metal absorb the energy from the light, and if enough energy is absorbed, the electron is released. This is what is known as the photoelectric effect, and the emitted electrons are called photoelectrons. The key points here are that for a given metal, no photoelectrons are emitted if the photon is below the threshold frequency. That is a very important term. Photoelectrons can have a range of kinetic energy from 0 to max, and this kinetic energy increases with the frequency, not the intensity, the frequency of the photon. Consequently, the amount of photoelectrons emitted per second is affected by the intensity, not the frequency. People commonly get these two properties mixed around. And also, before an electron can be emitted, it needs enough energy to break the forces holding it, and this is called the work function. Work function should be in italics there. Don't know why it isn't, but work function should be in italics. Very important term. And the work function varies between metal to metal. Let's finish off with a story. This story is about a bloke called Albert Einstein. Initially, the photoelectric effect was attempted to be explained by wave theory, but it just couldn't. Einstein's photon model of light made much more sense. What he suggested was that electromagnetic waves and their energy exist in discrete packets, which we know as photons. He saw these photons of light as having a one-on-one particle-like interaction with an electron in a metal surface. A photon would transfer all of its energy to one specific electron. And that's it. So let's talk about energy levels. First, you need to be familiar with the word ionization. This is the process of creating ions. You also need to be familiar with the term ionization energy, which is different from the chemistry one, but not by much. It's the amount of energy required to completely remove an electron from an atom in its ground state. Because if you just put amount of energy required to completely remove an electron from an atom, then that's not correct, because if the atom's slightly excited, then the amount of energy required is then slightly less, so you need to specify that it's in its ground state. Electrons in an atom can only exist in certain energy levels. N equals 1 is the ground state, however some exam papers may put N equals 0, but N equals 1 I assume is the standard. And electrons can in fact move up and down energy levels, just, whenever they feel like it. No, there are processes to it, and we'll go through them in just a minute. An atom in anything past ground state is known as in its excited state. And here we can just sort of see the energy levels and how much energy it takes. Here we have ground level at N1, and you can just see the transition block sort of decreasing as you go higher. So let's talk about excitation by collision. This is a form of excitation where an electron in an atom is hit by another electron. So an electron hits an electron with exact energy. It has to be exact, no less, no more. The electron then moves to a higher energy level. If the electron is actually moved to the point of ionization, this is called ionization by collision. To clarify, by the way, in case anyone, decides to be a smart ass, the collision isn't actually a real collision. Electrons don't actually touch. They just go near each other and repel, but for argument's sake, we call that collision. Next up is excitation by absorption. Here, instead of being transferred energy by colliding an electron is excited by instead absorbing energy from a photon. Once again, it has to be exact. But all in all, it's the same principle, really. But then, of course, we have de-excitation. Now, this is pretty cool. This is obviously the exact opposite of excitation. An electron drops down from an energy level and emits a photon of equal energy difference to however much it's dropped down by. And excitation and de-excitation is how we can actually explain how filament tube lighting works. Arguably the most defining factor of any classic Pakistani household. The human race, especially the brown members of it, love filament tube lighting. As a brown man myself and a scientist, I find them especially amazing, and it's because of how they work. The filament is heated, and then electrons are released as a result. A voltage is applied to the ends of the tube, which causes them to accelerate due to the current. Electrons then collide with the low pressure gas, whatever that gas may be, which causes excitation. Once they de-excite, photons are emitted corresponding to the energy change, which actually corresponds to UV light. Now UV light is dangerous, so the phosphorus coating on the filament tubes then absorbs the photons, and then those atoms are then excited, and then they are de-excited, and a photon is emitted corresponding to the energy change, which in this case is visible light, which is the light we see and love. Next thing I want to talk about is spectra. There's two types of spectra. There's continuous spectra, which contains all possible wavelengths, and there are no gaps in a continuous spectrum. Spectrum of white light is continuous. That's an example of continuous spectra. And hot objects produce a continuous spectra in the visible and infrared spectrum. In my notes, I have as invisible here. I'm gonna amend that. And this is basically what it looks like. A line spectrum, on the other hand, only contains lines of the wavelengths that are emitted. It's produced by white light when you put it through cool gas, and it's also produced by an excited gas. And different elements actually produce unique patterns of line spectra. This is actually how we discovered helium from the sun. This is an example of line spectra. I'm so sorry to fuck with your mind like this, but everything in this world is a wave and a particle, and there's proof behind it. Here's how we prove light has dual nature. On one hand, it's obviously a wave because it diffracts. As you can see here, it diffracts when it goes through a slit. However, we also know that it's a particle thanks to the photoelectric effect, as an electron absorbs all the energy in a light photon. We can also prove electrons have dual nature. Yeah, I bet you didn't know electrons were waves as well. Never thought you'd come across that term in your entire life. On one hand, it's a particle, obviously, because it can be deflected by an oppositely charged magnetic field, which shows that it has charge. You know, waves can't have charge. But we also know it's a wave because electrons can diffract too, as you can see here. Now, all this crazy crap was hypothesized by a man in the name Louis de Broglie. What a legend. As you could guess, he was also the man behind the de Broglie wavelength, which relates a wave property to a moving particle property. That's everything for today, guys. Have a fantastically brilliant day. I'll see you in the next video. Bye bye.